Okay, welcome to this morning session of our penultimate day in the conference. It's my great pleasure to introduce Vincenzo Mantova from Leeds, who will speak to us about updates on exponential algebraic closedness.
Thank you. Thanks for the organizers for inviting me. And actually, it's the first time I'm involved. So thanks for that. Thanks to you for coming. Half apologies to all the theorists who must have heard versions of this talk for a few times, not too many. But certainly the first part is going to be familiar, a little bit different. Okay, so the first part I want to explain what this problem is. Because I'm assuming quite a few people here they're just not familiar with it. Okay, so the problem, I can phrase it in this way. So I'm taking a system of equations and some variables. This is the tuple Z. And the system is going to look like this. I have a bunch of polynomials, 1 to ek, and the polynomials are evaluated in z1, zn, e to z1, e to zn. Okay, and sort of naive question is, does it have solutions or not in the complex numbers? Okay, so these PIs are polynomials with complex coefficients. Okay, does it have solutions? And this EAC question, this exponential algebraic closedness question, is a conjecture of Zilber. EAC conjecture it says that, well, if sigma satisfies, okay, and now I'm going to try to use a specific color for this. It's not going to last very long. It satisfies certain geometric conditions. Okay, and I will be shy about what those are exactly. Then there exists not Z, there exists an A bar such that it is a solution of the system. Okay, so you can find a complex number satisfying those, all of these polynomials at the same time. Okay, so of course the problem is, there are many problems, but the key idea here is that Zilber identified a good set of geometric conditions that make sense, and in some sense this is a sort of dual of either Schanuel's conjecture or Ax-Schanuel, depending on how you look at it. We keep debating whether what is the best framing in a more philosophical sense. But anyway, whatever this means, these are strong implications on at least on model theory of X, of complex exponentiation. So EAC definitely implies that this structure, the complex field with the exponential function, is quasiminimal. Okay, and you don't need to, I'm not going to write what this means. Quasiminimal means every definable set of C is countable on the complement of a countable set. Okay. So that's the kind of object you get. So for example, G, the reals, are not definable. This is true. Okay, so that's the kind of thing you get. You get more than that. Maybe I will mention it again just briefly. And now this is I should at least say who did the proofs of this. So Boris gave a proof in 2005, roughly of this statement, not quite this statement, with more assumptions, and then Martin Weissenberg gave a better sort of bigger argument that covers, that does exactly this. plus more general versions, like there's a version of this for the abelian exponential, and we mentioned that a few times. Okay. Now, again, nice. Now, how hard can it be to solve the system of polynomial equations? Right. Well, there's a threshold function in the middle, of course. So that's the main problem. So let me show you. Instead of trying to, be sort of general, I will just start with the simplest possible case, which is just n equals 1, and just one polynomial. Right? Okay. Now, how hard can this one be? Well, no. This is easy. Okay. So say that my sigma is just one variable, and the system is really polynomial. Inside that's z equals 0. Okay. Now this, I should warn you right away. This is the best possible case that you might ever get, and nothing is ever as simple as this one, right? Okay. So don't get I don't want to give you a false impression. This is going to be very easy. So this is best case. Why? So this is easy. So you just use, for example, there are a couple of ways of writing this, but automatic factorization is the easiest way to explain it. So say that it has only finitely many solutions, or maybe no solutions at all, right? Say only solution, just one is okay, C, and K could be 0. Okay, so I'm covering the case of no solutions as well. Then, just by complex analysis, not a lot of it, you get that this is going to be a polynomial, which is just the product of z minus zi, some multiplicity, which are the zeros of the function, and then what's left is just an exponential z with some d here. And this d is going to be the degree of p in the second variable. Okay. And well, then what happens? And now you have that the exponential function is transcendental over the rational functions of the C, right? We see Z. But that means when you look at this identity, this means that the polynomial P, as the polynomial into variables, is going to be y to d times a polynomial x. Okay? And it doesn't get more geometric than that, for my purposes at least. Okay, so this is the kind of geometric, this is the meaning of geometric I have in mind, to determine whether this system has solutions, infinitely many, finitely many, or maybe no solutions at all. You just look at the polynomial. If it is of this shape, then you know the answer. You know the zeros are going to be only the zeros of this cube. If it's not of this shape, then it has infinitely many solutions. Okay.
Can it have no solutions? Can it have no solutions?
Yeah, it's the case where Q is a constant. Yes.
Sure.
Yeah, because then it's, the exponential system is 0, right? So, so this is, so it's either, so yeah, you just check, I don't need to write this out, you just check whether P is of the shape, and you know the answer. Yeah, you know everything. And you can push it further, right? I mean, further, it's just to say how definite this is. This only depends on the coefficients of P. If, say, P is given to you with coefficients in a computable field, okay, you know everything, then you just check. You just compute the coefficients and that's it. So in a sense, this is even decidable because you can just do the calculation. Okay. Okay, this is not going to happen again, right? So let me now show you a case which is, it's going to sound a bit silly for the moment, best if I just mention this right way. Suppose now I have two equations, which is of course is too many in one variable. I have P1 Z1 into Z1 equals 0, and also some other polynomial P2. Why am I saying Z1? There's only one variable. No need for this. I have two equations, and of course it's already bad. I would say it's overdetermined, but also there are other more subtle problems here. So this could be something as silly as the first equation is that z is equal to 1, and the second equation is some polynomial in e to the z equals 0, and maybe, you know, well, of course, z equals 1, e to z is going to be a transcendental number, so how hard can it be? Well, this polynomial set coefficients in the complex numbers, so it's perfectly legit that this is, for example, a polynomial with coefficients in Q, in QP, in QPi, right? So maybe I'm asking you, does E satisfy a certain algebraic relation over pi? And, well, this is, let me say this is a decidable problem, right? So there is an algorithm to decide whether this is true or not, except that we're missing a big piece of information about whether E and pi are algebraically independent or not, right? If you believe that E and pi are algebraically independent, then this becomes trivial again, but we don't.
So this is a little bit unfair in that you're, I mean, in order to make a decidable question about this, you have to restrict the coefficients to some countable set, and then...
Yes. I mean, it has to be a computable field, and I'm arguing, right, that this is technically computable, but in the sense of, if you had this missing information, this piece of information, which is whether there is a relation or not, then you could do this, but you cannot. So even though, I mean, the problem is that the coefficients of the original equation are in Q. Well, not in Q pi, sorry, in this case. And this is computable, but the answer is, well, it's not with the current knowledge.
Okay, but you could say the same thing about regular even without the exponential, because you could just have you could have a polynomial, and I give you a number, and then I ask you whether that number is a 0 of that polynomial.
Oh yeah, absolutely, yes. This is not a new thing, right? And I'm just saying that this pops up if you just ask about exponential equations, because you have these problems. Yeah, I mean, my claim is going to be that the geometric conditions sort of remove all of these kind of issues, and you're left with something manageable. That's the spirit somehow of what I'm trying to say. So yeah, you can hit these problems, like problems with related to Schanuel's conjecture. I need to say Schanuel's conjecture at some point, so let me say this now. Schanuel's conjecture. This says if they Z1, Zn, complex numbers which are Q linearly independent, then the transcendence degree of Z1, Zn, e to Z1, e to Zn is at least n. Okay. So if you know this, you can do much more then you have tons of information, and you definitely can suddenly understand this problem very easily. In pi are going to be algebraically independent as that. Fun fact, I don't know how many of you know this, but the Android calculator, if you have an Android phone, your calculator is going to believe in Schanuel's conjecture. And it does calculations assuming this. Okay, so it tries to give you exact answers when you ask questions about E and pi and trigonometric functions, assuming Schanuel's conjecture, right? The argument was, well, if it's false, and we stumble on a counterexample, that's fantastic. So, but it's also never going to happen, right? I mean, no way this is. So yeah, only if you have an Android phone. Okay, if you have an iPhone, well, you're missing out. Okay.
Report if it finds a bug. Will it report if it finds a bug?
I don't know, GDPR, I don't know, maybe maybe they can't. Okay, so so this is one thing that can happen, and then it gets worse when I go to n equals 2. But it doesn't get a lot worse. Let's say now, I try to be more reasonable. I have two equations, where am I? Am I on time? Not so much. Okay, I have two equations, and maybe let me be more precise now. It's talking about the number of equations. So let the sigma be the algebraic variety defined by E1 x z bar w bar equals 0. Okay, so solving a system of equations means I'm looking for the intersection of this algebraic variety with the graph of x. Okay, and so the actual condition here is actually meant to be the dimension of this sigma equal to. Okay, so yeah, two polynomials, but they must be like independent of each other, and stuff like that. Okay, a bit more geometric, right? So in this setting, the EAC problem is mostly solved. Okay, with this kind of caveat. Okay, so there are a few cases. So the first one is if the sigma, if this variety is contained in this case, and 1z1 and 2z2 equals c for some n1 and 2 integers, not for 0 of course, and c some complex number. Okay, so if your variety, if your equations imply a linear relation between z1 and z2 with integer coefficients, well, then you need to be.
I lost the right track. What is the dimension v sigma equals 2? Is that an assumption or a case, or what was the?
Yeah. Sorry, it's meant to be like, instead of saying two equations, I want to say dimension of v. It's an assumption. I'm saying I'm looking at n equals 2 and dimension of v sigma equals 2.
Wait, but isn't the whole? I mean, n equals 2 means you have two variables.
Yes.
So.
I'm basically saying two variables, two equations.
Oh, I see. Oh, v sigma is okay. Sorry, I forgot what v. Okay, v sigma is not before you plug in.
Yes, exactly. Yes. Thank you. Yeah. Okay. So if you are in this situation, then actually you reduce to n equals 1, because I mean this is basically a change of variables. I mean, you replace z2 is something z1 after, but you need to do this after adding. I mean it's implied, but let me state this explicitly. You also need to consider that the exponentials are going to satisfy this additional relation. Okay, so the v sigma is containing this. So you can add this equation, and typically, generically, this is going to drop the dimension of the sigma by 1, because it's going to be a new relation. Sometimes it isn't, right? But it's an exceptional case. And then you use, you just do a change of variables and you use to n equals 1. And, who knows what happens, right? Something happens in n equals 1, and you have this kind of, well, we have an understanding of what goes on there. If otherwise, now we do two other cases. Now I take the projection of the sigma to z1, z2. Okay. So remember, b sigma is before plugging in the x. And I project down to the variables z1, z2. I forget about the values, the things that will go in the exponentials. Okay, now if the dimension of this is again 2, then we know the answer. Yes, there are solutions. And we can even say more, and they are, it's a risky dance, and I need to say what this means in V sigma. I mean, hopefully there's only one way of making sense of that sentence. By this I mean, if I look at the points, not the solutions, just the z's. If I take the points, so for each solution, I look at the point z1, z2, e to z1, e to z2, and I think of this is going to be a point on my V sigma, and I'm asking whether these points are the risky dense in V sigma. Okay, that's the minimum question I can ask about the distribution of these points in V sigma, and that's definitely the case here. So it's not just one solution, it's not just infinitely many solutions, actually spread out over V sigma. Okay, and this is a theorem of Branowell and Massa, 2017. Okay, and it's more general than that. I will mention this again, what do I mean by that, and then I'll also follow up. How do they do this? And this is, it's kind of, well, I mean, the method is just Newton's method. And I say just, I mean, you use a version of Newton's method for complex analytic functions that works well in this case, and they have a clever strategy for guessing where the solution of the system is going to be, roughly speaking, and for that they use the fact that the exponential function is periodic by 2 pi I. And so there is a nice trick where they say, well, I don't know where to go, but I know that if I change this number by 2 pi I, this part doesn't change, and this part grows. And that gives you enough freedom to say, okay, maybe I can go somewhere where I'm supposed to be close to a solution, and then they prove, yes, you're close to a solution enough that if you then know Newton's method, then you find an actual zero. Okay, and this allows them also to parameterize where the solutions, how many solutions you have. Basically, you start from any period, any multiple of 2 pi, any 2 multiples of 2 pi I for the 2 variables you have, and when they're big enough, you're going to find a zero somewhere close by. So it's a very explicit method, right? I mean, this is, you can basically compute the solutions. I mean, it is extremely very effective in the sense of computing things. Okay, this takes care of when this projection is dimension 2, when the dimension of this projection of the sigma is 1. Is it 1, is it 2 here? Okay. Then we can find infinitely many solutions. Okay, and this is me and David Massa, 23. Completely different approach. So for this one, we use the fact that, I mean, this projection of the sigma now, it's a curve. It's of dimension 1. So you have your solutions. If there are solutions, they're moving on a curve, and you're asking, and basically, I mean, you can easily reduce to asking whether a certain functions, a certain function on the curve, which contains the exponential function, has a zero on the curve. Okay. But that looks a lot like this case here. Okay, this was the case of I have a complex analytic function. Does it have zeros on the complex plane? Now I have a complex analytic function. Does it have a zero on the curve? Okay, so we do a sort of, this is a very abridged version of, I will say something we don't even say in the paper, but it's basically this is otherwise factorization on, well, algebraic curves. Okay, I mean it's a very restricted version. Like it's really this kind of factorization here. Just basically fundamentally things. If you want to do infinite products, that's not what we do. But yeah, you can get something similar to what happens here, and it's nice. We don't get the risky density, which is a bit annoying. Right, so there's the infinity menu, but whether they spread out across all of the sigma is sort of like, they should, but our method doesn't do that. We think it's possible to work any strategy. Well, nobody has done it. Okay, and if you notice, we've done n equals 2 completely, right? Because the dimension of this projection is either 2, 1. If it is 0, then you're back in the first case. Okay, your coordinates. Okay, maybe I should say, suppose that the sigma is irreducible, so you avoid maybe getting finite many points. No, say irreducible. But then you end up in the first case where you reduce to n equals 1. Okay, so that's the picture somehow of what's going on. If I go on and if I want to do n equals 3, then it gets more messy. Let's just say, I'll rephrase this, less predictable. No, this is way too vague, right? Let me just make an example. This is an example of two things at the same time, but to save time, I will just do this one. The question could be that it's telling you that e to z1 is equal to 1, e to z2 is equal to 1, and then there is a relation between z1 and z2. This is going to look awfully familiar to some of you, right? So this would be a case where b sigma, the dimension of b sigma is still 3. Okay, these 3 equations in 3 variables, technically speaking, but of course I'm cheating. Right? The 3 equations in 2 variables, that's one problem that you need to account for. The other problem is, if I spell this out, this is a completely different kind of problem. So z1 and z2 must be integer multiples of 2pi, i. So suddenly I'm asking about integer solutions of polynomial equations. Okay, this is I wouldn't call this a geometric problem anymore. Right? This is different. Okay, so this is kind of not what we're looking for. When I say we, I mean bodies. Okay, so now I can tell you, like the geometric conditions are about what was the color? Green. The geometric conditions exclude the bad cases. I mean, by which I mean the one I'm going to cross out. They exclude this situation. We don't want to have just an exponential being equal to a constant, because that's for reasons that's not a sensible thing, and it also prevents you from suddenly talking about integer solutions, which could be tricky. It also prevents this dimension dropping, right? This is actually 3 equations in 2 variables. You don't want that because it's kind of overdetermined. The geometric conditions will take account of that. It just says the dimension of a certain projection is at least 2 instead of being like 3 here. So this is not, this you can exclude, and you exclude this case here. Okay, two equations in 1 variable again. Dimension, we can say the dimension must be 1. So this one here. And you also eliminate this one. because it's a case where you reduce to lower dimension. So in some sense there is no point in doing that, but somehow this is what's sensible. Now it's a non-trivial theorem that, even though I haven't told you what the geometric conditions are, remove this stuff, you're left with only with things that in principle should be analyzable in this way. Okay, when you just look at your variety, you know, well, I mean, the conjecture is that you take your variety, you check this, the dimension of the variety is at least, you know, it's the number of variables you have, so it equals this n. And then you have all these projections, and you check that all of them have the right dimension. And the non-trivial theorem is that, for example, for these checks, you only have to do finitely many of them. And this is sort of one of the origin stories of the Zilber-Pink conjecture. It's about unlike intersections. But basically, these are definable conditions. Definable conditions, mostly in just ACF. In the language of rings, without the exponential function, that's the point. You just look at the variety and you check in dimensions. The one condition that doesn't fit here exactly is whether the variety is contained in a linear subspace given by rational coefficients. You need to quantify over these rational coefficients. And as far as we know, this is unavoidable. So there's one point where you quantify with the rationals, but at least for this analysis, it's fairly harmless. Okay. So this is what EAC.
So you can quantify over the rationals because you can define the integers
Yeah.
and therefore, yeah.
Yeah. So yeah, if I want to actually write maximization, which is what Boris does, in the structure, you can define the integers as the stabilizer of the kernel of exp, okay? Or you just divide by 2 pi I the kernel of exp, and then you have a copy of the integers, and then you can quantify over the integers here to say, I'm talking about varieties where this does not happen for every blah blah. Okay, so it is accessible. Like you can write an axiom in this structure because the kernel of exp gives you the integers, and I'm going to stop there maybe. People don't about this. How do you axiomatize the kernel of exp is z? That's well, I haven't told you that, right? And I'm not telling you to. You shouldn't ask. We can go there, but it's I say that it brings me off topic. Okay, so yeah. So now this is the moment where I'm trying to finish part 1, and I should tell you what the state of the art is before talking about part 2, which is this. And again, with the wave function. So what do we know? We know. Okay, and some of it is without there. This is a bit of exercise. Okay, so when you take your sigma and you project it down to, I hope this notation makes sense by now. I take the sigma, you know, which is a variety in the z bar and w bar. I project down to just the z's. If the dimension of this projection is n, is as big as possible, then yes, we know the answer. This is still grammar master, same paper. The strategy works in general. And I should say, right, this is also for abelian exp. Okay, and then to be more geometric, right? I mean, the exponential function of an abelian variety is not one function, it's like saying device plus p and its derivative to go into elliptic curve. But let me just say, you know, if you know what this is, you can work out what I'm saying. So this is true also in the abelian case. by the same method. 23. I think I know. But, and then also the J function, and this is work of Sebastian Eterović and Sebastian Eterović. Okay. So basically, this method of granular mass it's applicable to other situations where you can ask similar questions, right? For the abelian X, the question is basically the same, right? And the geometric conditions are basically the same as the one that Boris stated in his first work on this in 2005. You can ask a similar question for J. I'll get there in a moment. And then the geometric conditions are different because this is not an exponential function, right? This is a different kind of object, but similar enough. Okay. We also know.
But you're not going to tell us what abelian X is.
No, do you want to know what is it? No, okay. I mean, think. No, I can give you an example, right? So abelian X. By this I mean, I should be more explicit, right? For example, say the functions. I should write this projectively. So p prime 1 is a function from C to inside E2. The image, this is a morphism from, let me put all the information on the same line. This is going to be an analytic function, which is a group homomorphism from the additive group of C to an elliptic curve inside E2. Okay, so this is what I would call an abelian exponential. Okay, this is the exponential function of an elliptic curve in B2. And roughly speaking, you're taking a system of equations that contain Z, P of Z, and P prime of Z. And and you want to know whether it has zeros or not. Better version would be you take an algebraic variety in C cross E, C to the n cross E to the n, and you intersect it with the graph of the exponential function. That's a bit more precise as a way of placing it, but the style is the same. You take another abelian variety, it has its own exponential function, and you do the same thing. You can ask the same questions.
When you talk about abelian, you're only talking about elliptic curves, or are you also talking about abelian varieties?
No, abelian varieties. Yes, you can do this for any. You can do this for abelian varieties, and then, but then we're not very good at it. I would say personally, like. So this theorem here. So we said, we can redo the granular mass method, right, in a different way. Sort of, we're trying to make it easier to digest. We said we can apply this to the abelian setting. We can apply this. Our style also works for GM, for the classical exponential function. It also works for the product of GM and an abelian variety, right? So we can do split semi-abelian. The trouble is, we're pretty sure it works in the general semi-abelian setting when you have an extension of an abelian variety by GM in some way. But I don't understand them well enough. At some point, I need to know some growth estimates on things, and I just don't know where to get them. So yeah, but everything makes sense even in the semi-abelian setting if you want to be more general. And you can state the conjecture in the semi-abelian setting, and presumably this theorem applies if you can plug the right estimate in the proof. We don't have. If somebody can help me with that, somebody can tell me how the semi-abelian logarithm is shaped, right? Something concrete. That would be great. Okay. Okay. So. This is when the projection is maximal, then you have this kind of Newton method style of proof. When the projection of this sigma is 1, that's what we actually do. Okay, it's not just n equals 2, this works in general. No abelian version of it. Okay, this method is not as flexible as this one. So we worked out some special case based sort of well, it's in the air. Okay, now the big case that I have to mention, which is why this first part is we're not finishing. There's also work of Francesco Gallinaro, 2023. Philip mentioned this on the first day. This is the case where the sigma is a product of two varieties, and L is a linear subspace. Of C to the n. Okay, this is what we call raising to powers, because taking a linear subspace of C to the n is a bit like saying, it's a bit like taking the exponentials of, you should think of this as saying, for example, I'm taking the exponential of z and then the exponential of lambda z, where lambda is some complex number, not rational. Right? Because if it's rational, it ends up in one of those forbidden cases we don't want to deal with. So you can formulate it this way, and you're asking whether the exponentials of, basically you're asking whether the exponential of this linear space intersects an algebraic variety W. Okay, so you have to assume the geometric conditions, and this is based on using tropical geometry. So again, this is actually quite different. Okay, and you should acknowledge there were early results of Boris about it, but Francesco made it just more general. Okay, the nice thing about this result is that on its own, it gives you quasiminimality of a certain structure on complex numbers. So C plus times, if you augment it with these multi-valued functions, okay, so with this sloppy here, this is quasiminimal. The structure is quasiminimal. Okay, so we have some unconditional results now, like completely unconditional. This is a quasi-minimal structure. Okay, having defined the subset is countable or co-countable within C. I think I need to mention something else. Okay, so Francesco did also an abelian version of this. Again, by a different method again, because you can't do tropical geometries in abelian varieties. Abelian varieties don't go to infinity, they compact. So this doesn't make sense. And then he said, I know how to do this, and then he spent maybe 1 year on working it out. Something about what happens when you integrate certain differential forms on the abelian variety, and somehow having a zero is connected to a certain integral being positive. And the geometric conditions eventually give you that this integral is positive. So you can find zeros. It's vague, right? I haven't told you anything basically. But yes, there's this version. And see also, there's also work of Anna Dimitrieva on a special case of this, but with a different method. But not as general as this one. Okay, there's no proof of quasiminimality coming out of this though. Right. So this is roughly the state of EAC. Have I forgot anything? No? We don't know anything else, right? So it's a short list. Okay, so now part 2 in 10 minutes. It's always like this. With me, okay. So I was mentioning J function here. Okay, so the general philosophy is that whenever you have an Ax-Schanuel statement, whatever that means, if you know, you know, then you can formulate a exponential algebraic closedness question, right? It's not going to be exp anymore, but you can ask about that. And because we have a theorem for there is an Ax-Schanuel for J and its derivatives. Do you know why I stop at 2 derivatives? It's now me checking that how much people know. But this is because J satisfies a third order differential equation. So the third derivative is a rational function even of the previous ones. So it doesn't make sense to continue, right? I mean, this is where the information is. Okay, there is an Ax-Schanuel for these functions. So can we do EAC for J? Okay, and well, we can do n equals 1. Okay, and the answer is yes for n equals 1. But this time this is not. Well, it was not easy for us. There's some complications. So this is joint work with Aslanyan, Eterović. Okay, and this just actually came out 2 weeks ago. I mean, in a journal, right? I mean, we put a preprint 2 years ago almost. Okay. So now the question is, for n equals 1, what do I mean? Let P be a polynomial. It should be a polynomial for variables. Okay. Then P of Z, Jz, J prime Z, J double prime Z has. And now let me say, I will say in a second what this means. Has the risky dense solution unless P is divisible by y0 minus 1728, y1, and x minus c for some c. And of course, I mean, non-constant polynomial, that's another thing to get rid of. Okay. So what do we mean by the risky dense? Again, my V sigma now is this variety, Z, W1, W2, W4, 0. Sorry. Okay, this is a hypersurface in C4. So the polynomial gives you a hypersurface, something of dimension 3. And now when I look at the solution, each solution comes with 4 coordinates, okay, with a point in C4. I want to know whether this point has a risky dense in B sigma. Because that's what is predicted by doing a general EAC for J. So this is actually an important point. Like proving that this function has zeros is actually fairly easy. Okay, it's almost as easy as that proof. But proving that there is a risky dense in this hypersurface, that's where it gets more complicated. Okay, we can do this. Why do we have this very specific polynomial here? Well, this depends on knowing a bit about J. And I'm sure many of you know the number 28. Unfortunately, I knew that this would happen. I didn't have enough space. Bear with me. Bear with me. what is the J function? What is it doing? So by J I mean J, this is the invariance of elliptic curves. Okay, so it's a function that goes from the upper half plane, points with positive imaginary parts into C, and imaginary part into imaginary part, positive imaginary part. It satisfies, so for gamma matrix in Z, integer entries determinant 1, J of gamma tau is equal to J of tau, and gamma tau is Möbius action of the set to Z, Möbius transformation. And well, by the chain rule I can work out what J prime of gamma tau is. It's funny, right? It's C tau plus D squared, J prime of tau, and the second derivative, that's more complicated, that's C tau to the power plus D to the power 4, J double prime plus C tau plus D to the power 3, J prime of tau. Okay, these are the things you need to know. I mean, everybody will need to know a few more things, like the fundamental domain of this action. We've used it a lot. This picture here, and many of you have seen this. This point is I, square root of -1. This corner here is, we're going to call this rho. This is the cubic root of unity. Yeah. Special properties, we have that J prime of I and J prime of rho are both 0, and these are actually the only zeros of J prime, both these and their conjugates, because when you apply this rule, gamma of I and gamma of rho will also be 0. Okay. The second derivative of rho is also 0. And again, all its conjugates are 0 as well. And we have J of rho is 0 and J of I is 1728. Okay, so now, just with this information, I can at least tell you why this is the list of polynomials you must have here, the special ones. Because now we have that J, for example, J of I, well, let me just write this down. J of I is equal to 0, or Ji is equal to 1728, if and only if J prime of, oh wait, let me write down. For random tau, this is 0 if and only if J prime of tau is 0. Okay, but that means, so if my polynomial P is y0 minus 1728, then the solution tau, J tau, etc. also lies on the hypersurface where W1 is equal to 0. Okay, you need to maybe match up the variables I was using there with the ones here, but point is, of course, this lies in the hypersurface where y0 is equal to 1728, but also this one automatically. So you don't get a Zariski dense set of solutions, because all the solutions satisfy automatically both constraints at the same time. If you do one, you satisfy the other, and you're not Zariski dense in the sense that I was mentioning there. It just doesn't happen. So you need to say, when you have this polynomial, maybe even as a factor, I'm not saying p-reducible, just, I could have said that, but if for this polynomial this cannot work, so you need to exclude this case. And, well, and that's it. The theorem is basically, this is the only situation that really matters. For this one here, well, let's say exercise. Okay, you can work it out by yourself. Why is this not going to give you the risky dense things? I'm going to leave you as exercise. Okay, so how to prove this? Well, maybe I should mention a corollary, because apparently this wasn't known. Take you're looking at the set of taus in H, that are the zeros of the second derivative of J. And as far as we know, this set was not studied, right? I mean, there's no literature. Well, we proved that this set is infinite. Well, that was easy. I mean, we have this row here and its conjugates. But it has this risky density property in the sense that there are other zeros that are not conjugates of rho. And we have some very qualitative comments we can make about it. Okay, so now I've painted myself in a sort of metaphorical corner in the time. I want to say something about method, and somehow I never get to this part of the talk. I was sure this time I would make it. No, I didn't. But no, I can tell you a couple of things, and then I will be done. Okay, so what do we use? So methods, and just a list of 3 things. So one is elementary complex analysis. Okay, and I mean possibly even less sophisticated than Hadamard's factorization, right? There is a contour integral that we have to do at some point, and that's the most painful part of the paper because we need to do actual estimates, and I'm not used to those. Right? I like doing model theory and saying formulas and. But yes, no. That's, well, I mean, I don't like this. We don't like this part of the paper, but it gets the job done. So that's good. That's very basic. And I'm saying this now basically just for this audience. Very basic valuation theory. Okay, I'm almost sort of doing false advertising. At some point, there is valuation of rank 2. We take the functions generated by Z and JZ and introduce a valuation that can measure the exponential growth and the polynomial growth at the same time. And the best way of doing this was just introducing valuation. We almost don't say valuation in the paper because we sort of basic, right? So there is a Newton polygon if you want. And even that we do it by hand because it goes faster than explaining what a Newton polygon is. That's how basic it is. Okay. And then, almost trivial zero estimates. Okay, because at some point it's crucial in the proof that if you're given a polynomial in J prime, J double prime, that we're able to detect the multiplicity of the zeros it has, at least generically. So we take a polynomial in J prime, J double prime, we say, does it have a 0 tau or not? Well, let's move tau by a generic matrix in a set to Z first, and I want to know generically in this gamma what is the multiplicity of the 0. Okay? And most of the times, you get what you expect. Just by looking at the polynomial, how the polynomial splits into irreducible factors, you're able to say, aha, generically the multiplicity of 0 is going to be just the one you get from that. But it's not always exactly the case with the exponential growth that we get something annoying, we get this. So we have this valuation in Z squared, and we can say that the exponential part has to be the one you expect, but the other one can change, and that caused us a lot of pain because we could see the cancellation. Like, yeah, but it's not that bad, and it's not. So that's why it's almost trivial, but not quite. Okay, thank you. I'll stop here.